Hey guys, welcome back. This is 3.4 and 3.5. We are talking about carrying capacity and population growth and resource availability. Our learning objectives for today are to describe carrying capacity, describe the effects that carrying capacity may have on ecosystems, and explain how resource availability affects population growth. So first we're going to look at something called the exponential growth model. So when we talk about growth models, by the way, we're talking about a representation of how population sizes will grow over time and sort of the expectations of what will happen to them over a given period of time. Will they slow down? Will they increase, etc.? And so this model that we're looking at first is called the exponential growth model. It's also called a J-shaped curve, so you can see the J shape here. This is a very unrealistic growth model. It's highly unlikely that populations ever in nature have the ability to grow exponentially because generally there's some type of limiting factor or some type of limiting resource that prevents them from just growing and growing and growing. But nonetheless, this is a model you do need to know about, and it says exactly this, that once the population starts to grow, it'll have slow growth near the beginning, but then become very rapid and have no ending point. So that's the exponential growth model. Again, not really common, although I guess you could use the human population as an example of exponential growth because we haven't necessarily found any one resource that limits our population growth. So you could place the human population in this category at this point because we have experienced exponential growth, but it would be a temporary placement. The more commonly used growth model would be the logistical growth model, and this is also called an S-shaped curve. With an S-shaped curve, there is going to be some type of resource or some type of limiting factor that prevents the population from growing exponentially. What will eventually happen is the population will reach its carrying capacity, and that's always represented by letter K. Letter K will, or the carrying capacity will depict how large the population size will get. So the population size can never exceed the carrying capacity. If the population does exceed the carrying capacity, then we'll experience something called die-off, and we'll talk about that again, or talk about that in a slide or so. But what we're seeing here is the same thing we saw in the exponential growth curve, which is slow initial growth at the beginning, and then we experience very rapid growth, and then once we start to get closer to the carrying capacity, we will taper off and reach what we call an equilibrium, where the population size will just remain at a steady state. So eventually our growth is no longer exponential. Our growth is just steady state. We're losing, where people are dying, or whatever the species is dying, and it's being replaced by other individuals, but it's never actually becoming larger. And it's always going to be limited by whatever that resource is, and that resource can vary, and we'll talk about what those are. It could be food, it could be water, it could be space. It just really depends. For plants, it could be something like phosphorus or nitrogen. We talked about those limiting factors when we were talking about nutrient cycling, but every population has some sort of carrying capacity to it. Now, this is what I was talking about, overshoot and die-off. So you see here, what we're seeing here is the exponential growth curve. And then we see that at some point there must need to be a carrying capacity. And what you're seeing here in this model is overshoot past what the assumed carrying capacity is, and then massive die-off. So if you experience overshoot, you've overshot the carrying capacity, there's no longer a resource that's now available to everyone, and so now a large portion of the population has to die off very rapidly, and then you'll see the process start again where you'll see slow exponential growth, and then hopefully the carrying capacity catches it. So overshoot is going over the carrying capacity, and die off is rapid decline of a population due to death as a result of overshooting the carrying capacity. And so what we'd expect to see after die-off is back up with this exponential growth, perhaps some sort of overshoot, some die-off, and then this is called steady state equilibrium. It's where we're trying to determine where that carrying capacity is. So the population will fluctuate up and down, up and down. It'll undergo what we call an oscillation until eventually we sort of hover just right above this line, and that would be our carrying capacity. So it's usually populations will undergo this every once in a while. So sometimes maybe an abundance of food sources available. Say there's an increase in the vegetation due to a heavy rainfall year. Their carrying capacity may be temporarily increased as there's more food sources available. As the food becomes less abundant because there's no more rain and they've overeaten the vegetation, they'll experience mass die-off and will return back to that steady state equilibrium. So what are these things that are sort of affecting our carrying capacity? We can categorize these into either density dependent or density independent factors. So a density dependent factor is going to influence the individual's probability of survival and reproduction, but it's going to dependent on the size of the population that they are in. Whereas a density independent factor is going to have the same effect on your probability of survival, but it is regardless of whatever the population size is. So if that's confusing, let's take a look. So if it's density dependent, it means the relative quantity of individuals living within that area are going to impact the relative amount of impact, I guess, this will have on you as an individual. So these tend to be biotic characteristics. Generally, it's going to be things like competition for resources. So the more individuals are within the population, the higher the competition is. This would be density dependent. Levels of predation. Again, the more individuals within the population, the higher amounts of predation could possibly exist, or lower amounts, depending on how big the population size is. The higher the likelihood that there's going to be parasites or diseases that are spread amongst populations that could also cause a carrying capacity to be reached. But those are all going to exist. They're all going to play larger roles depending on the relative size of the population. And this is going to mostly affect the logistic growth of a population. So density dependent factors are what influence that carrying capacity. Whereas density independent has nothing to do with the relative size of the population. These tend to be abiotic characteristics, and they're going to affect all populations, all sizes of populations, regardless of size, regardless of density, all the same. So these are going to be things like natural disasters, severe weather, drought. It doesn't matter how big your population is, where you are within your carrying capacity. If a severe drought hits, everyone within the population is going to be impacted. So density dependent are going to be dependent on the size. So again, with something like predation, not every individual within the population is going to be affected by that. Higher levels of predation may exist depending on like what the predator-prey relationship is, but not all individuals are eventually going to get preyed on. Or same thing with like parasitism or disease. It may affect some individuals within the population, but not all of them. So I'll give you an example of a density dependent factor. In this case, the density dependent factor is going to be food availability. So this is an experiment done with paramecium where they put them in a controlled setting. In experiment number 1, we've got these paramecium that are given a very low food supply, and it shows them reaching their logistic growth curve very early on. So they do reach a carrying capacity, and no more paramecium are allowed to exist in this area because they've run out of food essentially. Whereas if we double the food supply, we see a doubling in the size of each of the species of paramecium. But again, we still see a leveling off. So it's kind of showing two things. It's one, showing that even if you double the food supply or you have more, you'll still reach a carrying capacity because eventually you will run out of food, so you don't see exponential growth always. But it does show that if you increase your limiting factor, then your carrying capacity can be, that your level for your carrying capacity can be raised. So I already kind of used these terms, but other factors that may contribute. So limiting resources. I kind of used the example already of nitrogen and phosphorus, but some type of resource could be food also, could also be a factor that contributes to a carrying capacity. And I don't know why I have carrying capacity here, but anyway, okay, I think that's it. Let me know if you have questions, and I will see you guys in class. Thanks.